Hi, welcome to the screencast for 10.5 and 10.6. 10.5 is just flat out hideous, but I'll see if we can try and simplify it a bit and help you get through the basics of it. And so that the next time you see it, probably at the college level, maybe it'll make a little more sense to you. But halogenoalkanes, the general formula is CN H2N, this should be a subscript as well, H2N plus 1, X, where X is a halogen. So it's an alkane with one halogen group substituted. Remember, if there's two halogen groups, we'd call it a dihalogenoalkane. So this is just one halogen. So this would form, remember, from alkanes with the substitution reaction. It usually involves initiation, propagation, termination. This isn't spontaneous reaction, so it usually involves homolytic fission. So this was all stuff we talked about back in 10.2, I believe it was, with the alkanes. The halogen can easily be bumped off once it's on there, which makes the halogenoalkanes an important group of compounds used as a pathway or a stepping stone to synthesize other organic compounds. So although halogenoalkanes themselves don't form easily, once they do form, they can be used as stepping stones or what organic chemists call pathways to other organic compounds. Halogenoalkanes themselves can also be used in products. They've been used a lot in propellants and refrigerants. Some of the earliest halogenoalkanes, CFCs, had 2-chlorine and 2-fluorines on the carbon. And they were a very bad idea, thanks Thomas Midgley, because that allowed the chlorine to break off in the upper stratosphere and start this whole destructive chain reaction involving chlorine-free radicals destroying ozone or O3. So the reaction that takes place when the halogen is substituted for on a halogenoalkane is called a nucleophilic reaction. And so on this page, I'm going to try and set you straight on some big words and again, try and simplify this. So think about the carbon-halogen bond. It's going to be highly polar compared to the carbon-hydrogen bonds. If you look at carbon and hydrogen, their electronegativity isn't so far apart, 2.20, 2.55, pretty balanced there. It's in a very symmetrical shape typically for a hydrocarbon. So very little polarity in the bond and very little polarity in the molecule. But once you put the halogen in, whether it's fluorine, chlorine, bromine, iodine, those are all much more electronegative than the hydrogen is. And now you're going to have quite a bit of polarity going on. So you have a very polar bond with carbon becoming positively charged, the halogen having the electrons more of the time becoming negatively charged. So when an atom picks up that positive charge, that is known as an electrophile. An electrophile just means they have an attraction to electrons, or it's a fancy way of saying positively charged. And then nucleophiles have a lone pair or have an abundance of electrons, so they have an attraction to a positively charged ion or substance. So really, electrophile and nucleophile are fancy names for positively charged and negatively charged. And of course, they're just the opposite of what you expect because phile means attraction. So attraction to negative means it's positive. And the nucleophile means attraction to positive, so it's a negative object. This is really exactly the same thing as Lewis acids and bases. Remember, a Lewis base is an electron pair donor. So a nucleophile is just a Lewis base. And then a Lewis acid is an electron pair acceptor or an electrophile. So again, nucleophiles are an electron-rich species. They're attracted to the positive things like a nucleus or a carbon atom that's got a positive charge resulting from a polar bond. So for example, NaOH could donate its OH group and substitute for the halogen group on any halogenoalkane. So looking at the simplest one here, you would have chloral methane, and when NaOH comes in, the OH could substitute for that chlorine and form methanol and then a salt. So anytime a base, and that's really the only reaction IB looks at with these nucleophilic substitutions, is having a base come in, you will form a salt and an alcohol. So we're going to take a look at this, and there's a couple possibilities here, because just like alcohols and alkenes, you can have a primary, secondary, or tertiary halogenoalkane depending upon where that halogen is located. So again, it usually involves a base or OH coming in, so it's going to form an alcohol, and the carbon is always going to be the electrophiler where that alcohol is going to attach the alcohol where the halogen was, so just a straight up substitution reaction. But these substitution reactions are called SN2 or SN1, and it's S sub N2 and S sub N1. And what that means is a nucleophilic substitution, which is bimolecular, or nucleophilic substitution, which is unimolecular. And I know it's just making it more complicated, but all it's really talking about is whether or not there's one molecule that limits how fast this reaction could go, or if there's two molecules that are going to limit that. And we'll look at this in more detail here. But primary halogenoalkanes undergo SN2 reactions, whereas tertiary halogenoalkanes undergo SN1. They're not really sure which happens with secondary halogenoalkanes, but they do know they can undergo either SN1 or SN2. The good news is any IB questions you see on this will likely involve a primary or a tertiary halogenoalkane. So again, the substitution reaction is via a nucleophile, so it's called S sub N. And again, the 1 or 2 depends on whether the rate is dependent upon 1 or 2 reactants. So let's take a look at this in more detail. SN2, remember, is with a primary halogenoalkane reacting. So I've got CH3Cl. It's the same equation I had on the first slide. But what I haven't shown you is that an unstable intermediate compound is going to form with both the chlorine and the hydroxide or hydroxy ions attached to the carbon at the 4th bonding site before the final products form. And this initial step is the slower step of the two. So going from the reactant to the unstable transition state is slower than going from that unstable state to the final product. So since this is going to determine how fast the reaction goes, and it involves both chlorine and oxygen, they are both going to be concentration of either of these ions can limit the rate, and that's why it's called an SN2 reaction. Two things can be involved in limiting the rate. So taking a look at this, CH3Cl, our original organic compound here, looks like this. Remember, the carbon is already going to be somewhat electron deficient because the chlorine tends to hoard the electrons. Over here, you could draw your NaOH separate because the Na really isn't going to be part of this, or oftentimes we don't even include the Na in here. It's up to you if you want to include it or not. But the intermediate step then is what I'm going to have both the OH and the Cl bonded on here, along with the other 3 hydrogens. And at this state then, I actually have an overall negative charge on this. So you use the parentheses and show that it's picked up an extra species and it's picked up a negative charge. And then, so then this is the slow step, or the rate determining step. Once you get this transition product made, then it very quickly will transition to the final product, which is our methanol or alcohol. And then your other product would be Cl minus, or you could show it as NaCl, either one. The other thing that IB likes you to show is where the electrons are being transferred here. So at this step here, this is where electrons are being transferred to the Cl, while at the same time the OH is transferring electrons to the carbon. So that's the action we tend to see. And sometimes they actually write this as a separate step. Back over here, I could have shown, so before they're actually both attached here, I've got OH trying to donate its electrons as Cl's trying to take the electrons. But that's the electron movement that goes on with an SN2 substitution reaction. Okay, looking at an SN1 reaction, I'm going to scroll back up and show you the actual reaction and draw this out as well. But just the notes that you won't be able to see as I'm sketching this out is a tertiary halogenoalkane is reacting in an SN1. And because there's 3 alkyl groups, remember that's what tertiary means, is that there's 3 carbons attached to the same carbon that the halogen is attached to. That's going to make it really hard for the OH group to come in and attack the bond, or for the nucleophile to come and donate its electrons. This is something known as steric hindrance. Steric just refers to the shape. And so this means the Cl must break off on its own and leave behind the CH3 positive species, and that's called carbocation or carbocation. And then this is the rate determining step, so it's only dependent on the Cl breaking off and leaving behind that positive species. So this is considered an SN1 reaction, because at this point the OH has nothing, the concentration of OH has nothing to do with how quickly this reaction will take place. So if we take a look at the SN1 mechanism here, I've got my carbon, my tertiary carbon. So there's a CH3 group here, a CH3 group here, and a CH3 group here, all getting in the way. So in order for this to occur, again, the electrons are going to be being pulled toward the chlorine. So I end up with CH3, 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 and a positive charge. And the chlorine actually pulled off as a separate ion. And at this point, the OH hasn't quite made its way there yet. But at this point, now that the chlorine is free, the OH would be beginning to move its electrons. But it's 2 distinct steps. So then the final product would form when the OH moves in and actually bonds with this tertiary carbon. And again, then you could show the Cl ion either being on its own, or if you want to show it as part of NaCl, that would be fine too. So slightly different mechanisms. Both involve electrons being transferred from the carbon to the halogen, and then from the hydroxy group to the carbon. So certainly a lot of similarities between the 2 mechanisms. So kind of one final note on substitution reactions among the halogenoalkanes is they both involve what are called a heterolytic fission, where a bond breaks and leaves 2 oppositely charged ions. And we've seen this a lot in replacement reactions, etc. And I just want to contrast to this with what happens when the halogenoalkane forms. When halogenos react with alkanes to originally form the halogenoalkane, it's a homolytic fission, and you might remember that term. And the difference is a homolytic fission is where it leaves 2 identical or 2 similar species, in this case a pair of free radicals. Heterolytic means you're getting 2 different ions, one positive, one negative. So just be aware of the difference in the terminology there. Then moving on to 10.6, you'll be happy to know I only have one slide for 10.6. 10.6 is about something called reaction pathways. And pathways, just what it sounds like, it's a path to another compound. So it allows a chemist to find a pathway to convert one compound to another by linking reactions. So let's say you start out with an alcohol and you need a carboxylic acid. Well, as long as it's not a tertiary or secondary alcohol, if it's a primary alcohol, you can go ahead and oxidize it under heat and reflux and get it to your carboxylic acid. That's a pathway. So page 10 shows possible pathways for the 7 different organic families that we've looked at in this chapter. Just to remind you, we've looked at alkanes and alkenes, and then from alkanes you can get halogenoalkanes and dihalogenoalkanes. We've also looked at alcohols, aldehydes, carboxylic acids, and ketones. So lots of different things we've looked at in this chapter. And just to finish up then, huge part of industry is finding ways to convert what we have a lot of to the things we need. So this goes on all the time in organic chemistry. And it's also a huge part of studying biochemistry. This is what goes on in your body all the time. One organic compound is converted to another. The ATP pathway is just one example of this. And these pathways almost all require at least one or more enzymes. To finish up the last two slides, I've just got some fun organic humor for you, and I'll leave you to discover that on your own.